Hi, this lesson is about the derivatives of logarithmic functions and about a technique called logarithmic differentiation. So before we talk about the derivatives of logarithmic functions, we need to remind ourselves of some of the characteristics of logarithmic and exponential functions, because remember, there is a relationship between these two. They are inverse functions of each other. So every logarithm can be rewritten as an exponential function, and vice versa. Every exponential can be rewritten as a logarithmic function. So I have, if y is equal to log base b of x, then that is the same as saying x is equal to b to the y. So one is a logarithmic function, the second one is an exponential function, but they can get rewritten in two different ways. So when your base b is e, that's a special type of logarithm called a natural logarithm, and we use ln to denote that instead of log. So if y is equal to ln of x, then x is equal to e to the y. So I point that out is because we're using the natural log more often, but there's another special one. When b is equal to 10, that's called a common logarithm. And so you would say y is equal to log of x. And notice that you don't put a little subscript there because it's implied when it's base 10. And if that's true, then x is equal to 10 to the y. Okay, but mostly we're working with natural logs. All right, so logarithms of any base have properties or laws, and these are really helpful sometimes when we're taking derivatives, so we need to remind ourselves of that. So if you have log base b of x to the n, this can get rewritten as n log base b of x. This is not a derivative. This is a relationship between the logarithm in its original form to the way it's written in the second form. They will give you the equivalent result by putting the exponent in front. The second one, regarding products, says that the log base b of x times y is the same as, gives the same value as log base b of x plus log base b of y. So the logarithm of a product can be rewritten as the sum of logarithms. The base would be the same on both sides. And then the second one, the quotient law or property here, says log base b of x divided by y is equivalent to log base b of x minus log base b of y, and that's as long as y is not 0, otherwise the whole thing would be undefined. And then just a couple things or attributes for you to remember. The natural log of 1, actually the log of any base of 1 will always equal 0. The natural log of e is equal to 1. In general terms, if you're taking the log base b of b, that's just equal to 1. And e to the ln of x is equal to x. And so that would be true of any base. Log base b of x would also equal just x. Okay, but no, usually you're using one of these. All right, so let's practice using our properties or our laws so that we get used to them or remind ourselves of how to use them so that when we use them with derivatives, they make more sense. So we're going to expand this logarithm here. It's a natural log. I have a product in the numerator. I have a quotient overall. I have two different variables, and both of them have an exponent associated with it. So you can see here that I rewrote square root of x as x to the 1/2. So I'm going to be using all three of these logarithms, logarithmic laws. And so that's what I did here. When you rewrite it, I have ln of 5 plus ln of x to the 1/2. So I used law number 2 above. I rewrote a product as a sum. And then minus ln of y to the 3rd. And again, it's a minus because I have a quotient. And then I took care of all of the exponents. So I applied the first law to get this final answer here, which is ln of 5 plus 1/2 ln of x minus 3 ln of y. So again, this right here is not a derivative. It's just practicing using the logarithmic laws to expand your logarithm and rewrite it in a different way. So that's something you would have learned in pre-calculus. Okay, so here's another one where, again, we're going to use our laws, but there's also going to be something that we could simplify. So expand and simplify as much as possible. So I have ln of e to the third divided by x. So I'm using the third law, which says that I could rewrite a quotient as a difference. So I have ln of e to the third minus ln of x. And then I put the exponent in front on this next line. So I have 3 ln of e minus ln of x. And then, as I mentioned a minute ago, ln of e is just equal to 1. So I did that replacement in the next line. So you're left with a final answer of 3 minus ln of x. All right, so now let's start talking about derivatives. All right, so we have derivatives of your logarithmic and exponential functions. So we have the derivative of ln of x is equal to 1 over x. So first thing you should memorize, it's a new rule for us. So whatever you're taking ln of, that would end up in the denominator. And if it's something other than x, like possibly an x squared or a square root of x in here, then you'd have to use your chain rule. But if it's ln of x, your derivative is just 1 over x. So in this case, x would never be 0 because 0 is not in the domain of your natural log. If you have a different base, like log base b of x, there's a change of base formula which allows you to rewrite it as a natural log. So it's equal to ln of x over ln of b. Ln of b is a constant, it ends up being a coefficient of ln of x. So it's 1 over ln of b times ln of x. So if I, again, am using the rule above, when you take the derivative, it'll just be 1 over x ln of b. So it's still using this original rule, but then just multiplied by the coefficient of ln of b. So it's written before because it just makes it easier to read. And then we have the derivative of b to the x. So that's an exponential function. And we have that the derivative is b to the x ln of b. And your b has to be positive, otherwise it would be undefined here. Remember what your domain is for natural log, it's all positive real numbers. So I'm going to show you how to actually derive this one, so you don't really have to memorize it, although you certainly can. All right, so to take derivatives of logarithmic functions, if possible, we first use the laws of logarithms to expand the logarithm and then take the derivative. That actually makes your computation of the derivative much easier. So this is an example of that. I want to find the derivative of this logarithmic function. So I have ln of e to the x 3x. So just a reminder, I'll use this in a little bit, but ln of e is equal to 1. But I am going to use my logarithmic laws to expand this, because if I took the derivative like this, I would have to use chain rule, and then within chain rule, I'd have to use product rule on this part on the inside. E to the x 3x is a product. So that would be kind of a longer process than what I'm going to do. So first I rewrote the y as y equal to ln of e to the x plus ln of 3 plus ln of x. So I used the product law, rewrote this product as the sum of 3 logarithms. But remember, ln of e to the x, well, that's the same as just x, right? Because ln of e to the x is the same as x ln of e. And remember, ln of e is 1. So that's just x. Then I have ln of 3 plus ln of x. So now this is what I have to take the derivative of, which is actually pretty easy because I just have 3 different expressions. Ln of 3, the one in the middle, is just a constant, and we know that the derivative of a constant is 0. And then I have to take the derivative of just the x and the ln of x. So that's what you see here. The derivative of x is 1. The derivative of ln of 3 is 0, so it's not there. And the derivative of ln of x, which was the definition I just gave you here, is equal to 1 over x. So that's your derivative. All right, so we're going to do another one here where we are again going to use our logarithmic laws to expand it first. So I want to find dy dt for y equal to ln of the square root of t plus 1 over t minus 1. So first let's discuss what you would have to do if I left it exactly like this. If I left it exactly like this, I would have to use chain rule. Ln is the outer function. The square root of t plus 1 over t minus 1 is the inner function. But then the square root function is the middle function. And the innermost function is a quotient, t plus 1 over t minus 1. So then I'd have to use chain rule. I would have 3 layers. And when I get to the innermost layer, I'd have to apply quotient rule to the t plus 1 over t minus 1. That would be quite a few steps and easy to get lost. So if I go through the trouble of applying the laws first, I'll be dealing with something easier. So first I'm going to apply the laws. So I rewrite the radical as to the 1/2 power instead. And then the first law says that I can put an exponent in front. Remember, this is still y, not y prime. And I can rewrite a quotient as a difference. So I get what you see here. Okay, so now it's expanded as much as possible and I'm ready to take the derivative. 1/2 is just a coefficient, so that just stays in front. And then I take the derivative of ln of t plus 1, that's just 1 over t plus 1. And ln of t minus 1, that's just 1 over t minus 1. And then I just have to do a little bit of algebra because I need a common denominator for this part right here, which is t plus 1, t minus 1. So the first fraction gets multiplied by t minus 1. The second one gets multiplied by t plus 1. So I'm left with, when I distribute this negative here, I'm left with negative 2 in the numerator times my common denominator of t plus 1, t minus 1. And don't forget, you just keep writing down that 1/2 in front. But then the 2's will cancel here. This one and this one will cancel. And your dy dt is negative 1 over t plus 1, t minus 1. All right, so here we want to find the instantaneous rate of change at the value of x equal to 6 for y equal to ln of 3x squared. Remember, this is just another way of asking you to find the derivative. And here, instead of expanding, I'm going to show you how you can just use chain rule. This inside part is pretty simple, so chain rule wouldn't be too much trouble for you. So when I take the derivative, you do 1 over 3x squared, that's the derivative of the outer function ln, times the derivative of the innermost function. The derivative of 3x squared is 6x. Then the 3 and the 6, well, they cancel. The x's cancel. So I'm just left with y prime equal to 2 over x. But then I have to evaluate it at 6, as stated, in the directions. And so you get that y prime, or the instantaneous rate of change at x equal to 6, is 1/3. All right, so we're going to move on to logarithmic differentiation. And this is a process or a technique used to take the derivative of a function where you take the natural log of both sides of the equation, then expand the function by applying the logarithmic properties as much as possible before taking the actual derivative. So this is the part that's new. You won't necessarily have a logarithm in the original problem, but you introduce the logarithm by taking the natural log of both sides of the equation. So it's a little bit different than things we've done in the past. So here's an example. We're going to use logarithmic differentiation to find y prime. All right, so first let's talk about what would you do if you didn't use logarithmic differentiation. If I had to take the derivative of this, I would have to use product rule because I have e to the 2x times x squared minus 5x to the 7th power. Within product rule, I would have to apply chain rule to the e to the 2x, that's a composite, and I would have to apply chain rule to the x squared minus 7 minus 5x to the 7th power. So it would be product rule and chain rule within product rule. And you would get the same answer I'm going to get with this logarithmic differentiation technique. All right, with this technique, as I stated above, you take the natural log of both sides. So I now have a new equation. I have ln of y equals ln of e to the 2x times x squared minus 5x to the 7th. All right, on the right side, I can expand this. So first, I rewrote the product as a sum of two logarithms. And then I used the first logarithmic law and put the exponents in front. Don't forget that this just becomes 1, so my first term is really just 2x. All right, so at this point, I'm ready to take the derivative. But remember, I'm taking the derivative on both sides, and in the end, I just need to solve for y prime. But my left side is not just y, it's now ln of y. So when I take the derivative, I have to treat ln of y as like a composite. The derivative of ln of y is 1 over y times the derivative of y, which is y prime. So on this side, I'm going to have to get rid of the y eventually because remember, you're solving for y prime in the end. On the right side, you can take the derivative of the rest of it in terms of x. So the derivative of 2x is 2 because remember, ln of e is 1. And here, it's 7 times the derivative of ln of x squared minus 5x. There you do have to use chain rule, but it's really pretty straightforward. It's just outer and inner. So derivative of ln is 1 over x squared minus 5x times the derivative of the inside, which is 2x minus 5. So I just have to simplify this piece of the problem, which is what you see on the next line. So I have 2 plus 7 times 2x minus 5 all over x squared minus 5x, minus 5. So I'm going to have to distribute the 7 across, and I'm going to need to combine these two in some way. So I need a common denominator. So the 2 gets multiplied by x squared minus 5x to have that common denominator. The left side still stays the same. And now here on this line, I distributed the 2 across x squared minus 5x, and I distributed the 7 across 2x minus 5. That leaves me with some like terms. So the right side simplifies down to this. Okay, but now I'm also interested in solving for y. So to solve for y prime. So to solve for y prime, I'm going to have to multiply the left side and the right side by y so that they cancel on the left and I have y prime alone. So I did that. I multiplied both sides by y, and that leaves me with y prime on the left. And on the right side, Well, I replace the y with what y is equal to. What is y equal to? The original problem. Y is equal to e to the 2x times x squared minus 5x to the 7th. I'm just going to shrink it down so you can see that I'm replacing the y right in here. But then that allows me to simplify a little bit more from this line to the next. The x squared minus 5x in the denominator and the x squared minus 5x to the 7th will cancel, and you're left with what you see inside the box. E to the 2x, I just put that in front, times the polynomial 2x squared plus 4x minus 35, and then the x squared minus 5x reduced to the 6th power, and you're done. So that was an example of logarithmic differentiation. Here's another one that's that works well with logarithmic differentiation. When you want to take the derivative of an exponential function where your exponent has a variable in it, logarithmic differentiation will allow you to find the derivative easily. So again, I just take the natural log of both sides, and then I rewrite it in terms of using the log laws. And so the first law allows me to put the exponent in front. So I have 3t squared ln of t, which means when I take the derivative, I'm going to have to use product rule, but it's pretty straightforward. So this is what I'm using. F is 3t squared, g is ln of t, f prime is 6t, g prime is 1 over t. So this is the part when we take the derivative. The derivative of ln of y is 1 over y prime. And on the right side, I'm just applying product rule. So I did f g prime plus g f prime. So that's what we see here. Then in the next line, I simplified. So the 3t squared times 1 over t becomes 3t. And in the next line, I just put the 6t in front. So I have 6t ln of t. It just makes it a little easier to read. So next step is multiply both sides by y so that I get y prime alone. But remember, the y is equal to the original problem. So I replace that y right here. So your final answer is what you see in the box. Y prime is equal to, in parentheses, 3t plus 6t ln of t times your y, which is t to the 3t squared. Okay, and here's one more using logarithmic differentiation. I want to find the derivative of y equal to x to the sine of x. Remember, when you have an exponential expression and your variable is in the exponent, logarithmic differentiation allows you to find the derivative pretty easily. So I take the natural log of both sides of the original equation, rewrite this side here using the logarithmic laws. So sine of x goes in front of ln of x. Then again, just like the last example, I have to use product rule. So from this line to this line, I'm taking the derivative. On the left side, I have 1 over y prime. On the right side, I'm using product rule. So I did f g prime plus g f prime. Then I just rewrote it in a different way. I put sine of x times 1 over x is just sine of x over x. This is not a limit, so do not make this is not equal to 1. I've seen many students do that over the years. We're finding a derivative. We're not evaluating a limit. So now from this line to this line, I got a common denominator for sine of x plus ln of x cosine x, which means this one got multiplied numerator and denominator by x. And then I also multiplied both sides by y so that y prime is alone, and I replaced the y with what y is equal to in the original problem, which is x sine of x. So your final answer is in the box. Okay, so that's it for this lesson. The lesson is on the derivative of logarithmic functions. Sometimes you can take the derivative very directly. Other times using the logarithmic laws makes things easier, and also the technique of logarithmic differentiation. Okay, so that's it for this lesson. Give the homework a try.